How good are the results with Paya? Um, they are okay, I guess. I think, yeah, maybe some of the results in the paper, maybe a little bit cherry picked. If you try it out yourself, it's not as good as maybe they're claiming. But I think, I think it's the more interesting thing is just like it's a very simple model, and there's a lot of potential for it down the line. Scaling it up and things like that. So I think that's why it's very interesting. Um, so yeah, I think a lot of these sorts of models at the smaller scale didn't do particularly well anyway. But I think with better data and with more training and such, I think it might have a better chance.
Cool. Yeah. I was not able to kind of get those results with the same prompts and stuff. Yes, I was wondering if it was just me or if I was missing something. But yeah, it sounds fair. First in kind of the line of the easy convolution kind of replacing the transformer stuff. So yeah, it's interesting.
Yeah. Looks like Jeremy's here, so briefly mention, like, yeah, so I mean, originally I was planning to actually talk about latent diffusion and stable diffusion this week, but I decided like maybe it would be better for like the author of the paper to talk about that. So he mentioned that he wasn't free this week, but he's free in a few weeks. So I figured that's probably more valuable than me talking about this paper, and instead having the author come and talk about it and talk about latent diffusion and stable diffusion. So that I figured, yeah, this week should be something else. So just letting you know that, yeah, in a few weeks, hopefully we'll have a nice talk by the author, Robin, and he'll talk about all that cool, all the cool stuff with stable diffusion. So in the meantime, we'll be talking about some other papers. And luckily, Jeremy was able to, I guess, put together on short notice a presentation on this, or to talk a little bit about this paper. So this is a paper that was released just this week, so it's like really cutting edge, fresh off the press work that we're talking about. So should be pretty interesting.
And Tanish, could you dig up Pedro's Hugging Space?
Yeah, I can do that.
Hugging Face space.
Yeah, I can put it in the chat. Yeah.
Great. Okay, so the paper we're looking at today is called Fast Text Conditional Discrete Denoising on Vector Quantized Latent Spaces. And I guess one of the first things that might strike you when you look at the paper is that the none of the people involved are from institutions that we're probably familiar with. One person is an independent researcher, and the lead author is actually somebody who describes himself as a YouTuber. The second thing you might notice is that they've taken on the big challenging task of conditional open domain image generation, which is quite the task to take on. Both basic prompt-based approach, but also image variations, latent space interpolation, structural morphing, and outpainting. So yeah, it's a big, bold paper for people that are not from big institutions, or and so Dominic at least doesn't have any other papers to his name at all. Oh, let me also mention, I quite like higher levels of interactions when I'm talking. So yeah, if anybody like either has a question or just a thought, my preference is to hear them as I go rather than wait till the end. So please do unmute yourself and dive in anytime. So our friend Pedro Cuenca has been kind enough to fire up a Paella. So Paella is the name of the model that this paper introduces, a demo. So we could try things that they have suggested. A beautiful Bavarian image with the Alps in the background. A beautiful Bavarian village with Alps in the background. Generate and go. So the second thing you might notice is that it did that 4 images in 3 seconds. So it's super fast. The third thing you might notice is that it doesn't seem to have a great sense of where objects start and finish. At first glance, the kind of houses look okay, but then you realize that there isn't really separate houses, but kind of one jumbly housey kind of thing. It's like a house cancer or something. For some objects like mountains, that works fine. But for others like astronauts and horses.
What resolution is this? 512?
Do you remember, Tanisha? I'm not sure what this particular.
Someone put in the comments 256. Someone put in the comments
Okay.
256.
All right.
Like, and this can generate high resolution, I believe. Yeah, so this is not great, obviously. So they've taken off a big bold project, and they've been more successful, I think, than other people I've seen with similar amounts of resources or background, but they haven't quite nailed it yet. But I think it's very interesting to look at, to see how they've got this far and consider how to go further, or whether it's worth going further, because I mean, it's incredibly fast. So the first thing I'll mention is that the model that's doing the generation is a convnet without any attention. And possibly that's what we're seeing here. You know, like often when you don't have attention, this is kind of what it looks like, is things are not able to have parts that refer correctly to other parts. So maybe it's that. Yeah, and maybe it's kind of like better at the moment for these more image reconstruction, outpainting-y, in-painting-y kind of things than generating stuff from scratch. Because they, you know, like something like structural morphing, you don't have the same problem of needing all the pieces to actually line up correctly and have the right number of legs on your horse and whatever. Okay, so how does this thing work? So I think the next thing I'll point out is the section called method, which tells you how it works. Starts at the very end of page 3. And so it basically covers all of page 4 and half of page 5, and it's finished. So it's not complicated. It's basically, yeah, less than 2 pages, which is cool. It basically looks an awful lot like, you know, stable diffusion or latent diffusion or whatever. It's going to look very familiar. Oh, have you guys done latent diffusion yet?
No, that's the we
Oh,
want.
that
That's
was the
why.
one you're going to wait for until
Yeah,
you get
yeah.
Robin.
Yeah.
Okay. All right. I'll give you a sneak preview then.
Yeah.
Okay. So here's the basic idea. I guess I should draw. I can only think when I draw.
Just a quick question. Are there other tools that are similar to this, but for other models? I'm just trying to like place how well the generation of this is compared to some of the other methods.
It's kind of hard, right? Because you kind of have to compare it to other things that have trained for a similar amount of time and have a similar amount of inference time. You know, I'm not an expert. I mean, maybe you know, I don't recall seeing anything trained for this long with this amount of inference time that can get anywhere close to doing what this is doing, but that definitely doesn't mean it doesn't exist. Has anybody else seen anything like that?
All right, yeah, fair enough.
How long was it trained for again?
So it basically did lie on 5B for 6,000 steps. So basically did about, you know, one of each image in Lion 5B.
Oh, yeah, we could. No, Stable Diffusion was trained some of the earlier checkpoints for, I think, only slightly more time, or maybe 2 or 3 times that.
And then, yeah, sampling steps is 12. Number of parameters is about 500 million.
They say 50 sampling steps for Stable Diffusion, but we can always decrease the number.
That's true. Okay, so let's get rid of this thing. So our basic diffusion process is like, if we're doing MNIST, for example, would be to start with a digit and then gradually add noise to it. I mean, not gradually in practice. In practice, we just add varying amounts of noise to it. And then we train a model where we give it, you know, varyingly noised amounts of images as the input. And the target is either the denoised version or the input minus the denoised version, so the noise. And so if we have a loss function based on a neural net that takes this input and compares it to the target, then over time, that neural network is going to learn to generate the target from the input. Now, in the case that, and of course, what we do in practice is we don't then run that model once during inference. We run it a bunch of times. Each time we just remove a fraction of the noise. Okay, so obviously I'm not going to go and recover all of that again, but that's a basic idea. Now this is fine for MNIST because it's 28 by 28 by 1. But, you know, if you want to do, well, let's just do 256. If you want to do 256 by 256 by 3, that's a lot of computation. So the idea is like that we could compress this 256 by 256 image down to something dramatically smaller. And generally speaking, the way we say how much smaller is we take one of the edges and we say how many times do we make it smaller. So we could make it 8 times smaller, or we could make it 16 times smaller. And we would refer to one where each edge is 8 times smaller as F8. So factor of 8, the F is factor. So it could be F8 or F16. And generally you would also increase the number of channels. So if we could reduce this to 32 by 32 by 4, say, that would be a lot less computation to do. So what if we could, yeah, compress every image in our training set down to 32 by 32 by 4, and then run the exact same stable diffusion, or the exact same, you know, DDPM or DDIM or whatever diffusion process as before. That would be great. So we have ways of compressing images, and the simplest way is to train a model. Again, I'm just going to keep using MNIST digits for now, even though MNIST digits are small enough, you probably don't care. You train a model where there's a, so let's say this is 28 by 28 by 1. You train a model which has a bunch of convolutional layers of stride 2. And so if you put it through 2 convolutional layers of stride 2, you'll end up with something which is 7 by 7, and you can choose how many channels you have. And so you have a model that has 2 stride 2 convolutional layers, or a bunch of convolutional layers, 2 of which are stride 2, and you'll end up with something smaller. And then you could do exactly the opposite. You could have a bunch of up sampling layers or transposed conv layers or whatever. So they make it bigger again. So like the really easy way to do this is, for example, just to do literally make 4 pixels where 1 pixel used to be, and then have a 1 by 1 conv, or you could have a transposed conv. But in that case, yeah, exactly the opposite would happen. You would end up back with a 28 by 28 image again. And so what you could do is you could train a model that takes your number 3 as an input, and the thing that gets spat out, you would compare to the input, and you would say, I want these both to be the same. So just MSE or perceptual loss or whatever. So this model here, well, actually the model is just this bit. This model here would be a model that learns to reconstruct its input after you train it for a while. Hopefully it spits out exactly the same thing you put in. So why is that interesting? Well, it's not interesting of itself, but what you could do is you could now cut this model in half, right? And run just this bit, which is called the encoder. And if you run just that bit, then after you've trained it, you're going to end up with every image turned into a 7 by 7 representation, something smaller. And then you could send all those images off to your friend over email or whatever. They're going to be much smaller, they're going to be compressed. And as long as they have a copy of the decoder, which is the other half, they could regenerate the original images. Now it's going to be lossy, right? It won't be perfect. But because images do kind of live on a lower dimensional manifold, which is to say, like, you know, random Gaussian noise wouldn't be a reasonable image, for example. You can compress these things, you know, if internally it might be kind of saying like, oh, there's an edge here and a corner here and a gradient there and so forth. So this, something which can do this recreation of an image after compressing it down is called an autoencoder. Okay, so we could use an autoencoder that takes our 256 by 256 by 3 images and turns them into 32 by 32 by 4 images by just running the encoder part of an autoencoder. And then we could do our entire diffusion process on those compressed images. And so that would not be generating, you know, noisy versions of the image anymore, but it'd be creating noisy versions of the compressed representation. And then after going through the entire reverse diffusion process during inference, creating the denoised compressed representation, you then can put it through the decoder and you'll get back an image. And so I mean, there's a few names we can give this thing, but the compressed representation generally seems to nowadays be called the latents. And so this idea of compressing your data first using an autoencoder's encoder, and then doing all the training, and then at inference time, doing things on the latents, and then running the result on a decoder is, broadly speaking, what latent diffusion refers to. Does that make sense so far?
I think that was a good, great explanation. It's like now we've
Okay,
already talked
great.
about it now.
There's so there's in the PyTorch examples repo. So if you go to like PyTorch's GitHub repo, GitHub organization, there's an examples repo, and in the examples repo, there's a bunch of examples, and one of them is called VAE, and this is an example of like the next level of thing we need to understand this paper, which is a variational autoencoder. And I quite like looking at code to understand these kind of things. So this is a variational autoencoder for MNIST, and it's the simplest possible one. They don't even use convolutions. So 28 by 28 is 784. So they're going to create a VAE neural network, which takes as input a 784 long vector, which is all the pixels of the digit, spits out 400 hidden activations. That's here, right? And then puts it through a ReLU, and then takes those 400 hidden activations and then turns those into 20 output activations for the encoder. Okay, so that's the encoder. But there's actually two layers which are both separately called for the encoder, and it returns a tuple. And why is that? That's because this is not just an autoencoder, it's a variational autoencoder. And a variational autoencoder is different because what it does in its forward is it calls encode, just like a normal autoencoder, and it gets back, you know, the latents, if you like. But it also gets back a kind of confidence about, for every one of those pixels, about like how confident am I about that pixel in latent space. And so this is the log variance. So like there's nothing special about it, right? They're just two different linear layers. And it literally just returns a tuple of those two linear layers, both applied to the first linear layer's value. But what we then do in the forward is we don't just say, here's the latents, but instead we call this thing reparameterize. And what that does is it gets a normally distributed random variable with mu, the mean of like, you know, the prediction, and standard deviation of also the prediction. So this is log var, so you have to go square root of e to the power of, or e to the power of 0.5 times, same thing. And so this is kind of weird, right? The inference or the forward is actually returning a random thing. So something that's kind of cool about this is that the random number is not dependent. If you look inside the parentheses here, it's not dependent on the input at all. So that means the derivative of this, like there's no derivative to worry about. So we can still backprop through this thing. So that idea is called the reparameterization trick. I don't know, it's almost too obvious to be a trick, but it's just saying that the line of code that calculates the random number does not include the inputs at all. Okay, so why is this interesting?
And to clarify, we've
yeah,
seen this also for diffusion models too, because like the same trick is there in the diffusion models where we have the mean and the variance, and we sample using this sort of similar trick. So yeah, just pointing that out. There's
great. Okay, so I'll go a little bit more quickly then. So did you guys look at this code? It's kind of like, I think it's really helpful code for like, it's so simple.
We didn't look at this specifically, but again, just a similar sort of thing, maybe in the context of diffusion models, we've maybe talked about a little bit, but yeah, I mean, this is still very helpful to go in more depth, obviously, but just wanted to, orient everyone else. Like we've kind of seen this already as well with some of these tricks, but yeah, but it's useful to still go over it. Yeah.
So one curious thing about this is that the forward function does the encode, it generates the normal random variable version of that, calls decode on that, but it doesn't only return that, it also returns the two things that were returned by the encoder. And why is that? Well, the reason for that is that they're actually part of the loss function. This bit here is binary cross entropy, which is what we're familiar with. It checks whether the reconstructed x, right, which is this, is the same as the actual x. So that's fine. That's just normal. But why is that not enough? Well, that would be enough for an autoencoder. But for a variational autoencoder, we actually want to make sure that all of the latents are of the same scale, basically. And so the way we do that is we say, okay, we want the mu to normally be 0 and standard deviation to normally be 1. And so this KL divergence term here, if you spit in a mu of 0 and a standard deviation of 1, you'll see that gives the lowest, well, the highest of this, or the lowest of the negative of this. And so what that means is that the model is being encouraged to create a mean 0 unit variance distribution of latents. But it doesn't really want to have a high variance on its latents because it's literally randomly generating them in the forward function. So it wants the variance to be as small as possible. So the BCE wants a small variance and the KLD wants a unit variance. And so what that means in practice is that the model is going to have to kind of like allocate its confident bits, to those pixels where it's highly confident, and not to the bits where it's less confident. And what that means also is that since there's actually a random number in the forward function, it's a more resilient autoencoder, because it doesn't have to be this exact value of the latent. It can be a little bit more than that, it can be a little bit less than that, and it'll still give the same answer, which is obviously what you want, right? So that's a variational autoencoder, and to train it, it's literally just the normal lines of code with the slight surprising bit, which is that we have a 3 tuple coming out of our model that has to be passed to the loss function. So, okay, so why are we talking about that? We're talking about that because the both Stable Diffusion and Paella use variational autoencoders. The Stable Diffusion as Robin will explain when he comes, much better than I can because he made it, does basically exactly that. It's a variation on autoencoder where the autoencoder is not just trained on MSE to regenerate the original images, but also has perceptual loss, and I think it's also got a patch scan loss, and they try to make sure it's super good. Paella uses a different nifty trick, which is the VQ trick, to create something quite different, which I think there's a drawing of it somewhere here. Yes, there is. Which drawing should I start with? Okay. All right, this should look pretty familiar based on what I just described. Here's the picture coming in, goes through the encoder and creates some latents, and then goes through decoder. But there's something weird about these latents, which is that they have a smaller height and width, but they have like one channel. So like what happened there? How come there's one channel? And also like what's with these different colors? Well, what this is trying to show is that this matrix, this smaller matrix, is actually a matrix of ints. And specifically they're a matrix of ints with 8,192 possible values. And this is what's special about a VQ GAN, is it quantizes the encoded version. So in other words, we don't just end up with our encoder giving in this case, for each one, it's going to be 20 long vector of floats. But instead, we're going to have a bunch of ints. Now, conceptually, those 8,000 odd, 8,192 ints are actually going to be categories. And each value is going to represent a different kind of thing. And so the idea is that you can represent a picture as basically saying what kind of thing is in each of these locations. And that's that's what we mean by quantized. So maybe the best way to explain this is to just show you kind of mathematically or code-wise what happens. And please, anybody jump in anytime if you've got ideas about how to express this, because I've not really explained it before much. Let's draw their version in the paper here. They've got the image. Okay, this is our image. And they've got this series of stride 2 convolutional layers or something like that, which turns it into a smaller version of the image. So maybe this is 512 by 512 by 3. And maybe we get it down to like 32 by 32 by, oops, 32. Tanish, do you remember how long the vectors in the code book are?
I think it was it 768? I don't remember exactly.
Yeah, let's just guess.
If it's the original
Whatever.
VQ GAN, the code book was 256 dimensions.
256, cool. Thanks, Kat. Okay. So if we now chucked a decoder right there, we would have ourselves, and if we also were spitting out standard deviation and doing the reparameterization check, we would have a VAE, or without that, we'd have a normal autoencoder. But we're going to do something else. We're still going to try to regenerate the original image. But we're going to make this harder for it. And what we're going to do is we're going to create an embedding vector over here. Here's our embedding vector, which they call the code book. but you use an nn.embedding. It's just like literally an nn.embedding. But in this particular context, they call it a codebook. And that contains 8,192 rows. And each row contains each row contains a vector of 256 long. So it's an 8192 by 256 rank 2 tensor or a matrix. And what happens is we take every single one of these 32 by 32, we'll call them pixels, even though they're kind of in latent space. So each one of those, here's one here, this is a 256 long vector, right? Because that's the number of channels it has. What we're going to do is we're going to find in our embedding matrix which one of our 8,192 vectors is closest. Just I don't know, using Euclidean distance or whatever. And maybe it turns out to be this one. This is the closest one. And so then what we're going to do is we're going to say, oh, well, each of these has a number. This is 0, 1, 2, right? So we're going to replace that whole vector with the number of its nearest, if its nearest vector from the codebook. So we now have 32 by 32 matrix. It's not a rank 3 tensor anymore. And this here would be, for example, the number 2. And so you could now convert that back into this by looking up all of those in the embeddings. All right, so we could now go and say, okay, let's go back and find number 2 in here and put it back over here. And so now we have again our 256 long vector. And so now we're back to a rank 3, 32 by 32 by 256 tensor. Now, notice that this tensor here and this tensor here are not quite the same. And the reason they're not the same is that the codebook isn't going to exactly have probably any of, or certainly not all of, these tensors in the original. It's just finding the nearest one. So this, this version over here is going to be similar to the thing that our encoder created, but a little bit different. And it just depends how close our codebook happens to be in terms of whether it has vectors that are similar or not. All right, having gone through that process, we then just go through the transposed comms or upscaling or whatever as per usual. So in other words, this bit here, the decoder, and this bit here, the encoder, are just normal autoencoder bits. But this bit here in the middle, the quantization, this is new. So there's two things I guess we have to discuss. One is why the hell do we do this? And the other is how the hell do we create the codebook? Let's do the second, because I think it's reasonably straightforward, if weird. To create the codebook, this is just part of our model, right? We just consider this nn.embedding module here is just part of our model. It's a terrible way to draw it. So if we kind of had our model, this is part of the model. So there's an nn.embedding module in there. And as always, initially it's a random matrix. And when we then train, we're just training it just like a normal autoencoder or a VAE, we want the embeddings in the embedding matrix to be close to the encoded version, the 32 by 32 by 256 encoded version of the image. And we want the 32 by 32 by 256 encoded version of the image to be close to the embeddings. So what you'll see in the math is they create this function they call SG, which stands for stop gradient. And they basically say that the loss function includes two terms. SG of, let's give these things some names. Let's say this vector there is X, for example, and the codebook vector found here, let's say we'll just call that Y. It would basically say SG of X minus Y, I think it's just squared, plus X minus SGY squared. So basically, if you ignore the stop gradient bit for a moment, it's saying part of the loss function is try to get the latents as close as possible to the codebook and the codebook as close as possible to the latents. You can't really do both at the same time. Like it doesn't kind of work out. The math doesn't just work out that it's like, or how on earth do you do that? So instead what you do is the stop gradient just says like, it's like saying with torch.nograd in, or doing detach in PyTorch. It's basically saying calculate that same loss twice, once where we update the codebook and once where we update oh, I got these backwards. The encoder.
I was under the impression that the main reason they did the thing with the stop gradients was they wanted to weight the two halves of the loss differently.
Oh, is that right?
Yeah, I think they're actually the same if they're weighted the same as the version without the
Okay.
stop gradients, but
Cool. I didn't realize that.
one or the other of them, I forget which, and VQGAN actually got it backwards to begin with, has like a term of 0.25 in front of it, a factor of 0.25 to weight it differently.
I see.
However,
I see.
given that you can get it backwards and still have it work, I'm not sure it's that important.
Yeah. Yeah, I mean, I would say don't worry too much about the stop gradient thing. Like you can just think of there as being a part of the loss, which is basically X minus Y squared. Okay, so why is this interesting? It's interesting because for the VQGAN encoder, well, the whole thing, to do a good job of reconstructing all the images, it's going to need to come up with a codebook that can represent with just 8,000 vectors all of the kinds of concepts that you would expect to see, that it does see in the images, such that then it can combine those concepts in this latent space, in this 32 by 32 matrix of ints, into something that it can then run the decoder on. And it's kind of amazing that that's possible. I mean, this is a very small, it's a very small representation. And I think, yeah, I think some VQGANs, like, so this VQ thing is used not just in VQGAN and Paella, but it's also used in some of the big models, like I think Party and Dali use it, and they have like 16,000 rather than 8,000. But they're still pretty small code books. And I think that's interesting because what it means is that it's now going to do, so as it says here, stage 1 is VQGAN. So it's going to create these very compressed versions of the images. And it's then going to do a pretty standard diffusion process on the matrix of ints, which is what they refer to here as Paella. This is the diffusion process. And it can be done conditionally using a clip encoder, which is what this C is. There's a few things to note, though. If we want to do a diffusion model on ints that represent categories, we can't apply Gaussian noise to it because they're categories. So instead, they have this thing they call a noise mask, where they just randomly grab a few of these latent pixels and replace them with some other random category, some other random code from the codebook. And so rather than like increasing the Gaussian noise, you increase the number of latent pixels that get replaced. So that's what this noise tokens is. So here's this original encoded version that they then replace some of those codes with random other codes. And then the Paella model is meant to guess what the denoised version is. Just like, in Stable Diffusion or in certain versions of like DDPM or whatever. Some try to guess what the noise is, some try to guess what the original is. Doesn't matter really. So then, yeah, for inference, it's basically exactly the same, normal reverse diffusion process, basically, where you try to, you're given a bunch of random ints between 0 and 8192, 32 by 32 or whatever it is. And you have to try to, the model then has to guess what the denoised version is, and you do that a few times. So that's all basically identical to latent diffusion, except for this quantizer. Now, what's interesting, though, is if you do it on the quantized tokens, you can do it much, much more quickly. And it's also much less kind of flaky, or it's much more resilient. With Stable Diffusion and those kinds of models, you have to make sure you remove exactly the right amount of noise at each step, otherwise you end up with, a pure white or pure black image, or you'll end up with something that's really, really out of focus, or you'll end up with something that's basically the mode in latent space or whatever. Paella doesn't have to worry about any of that. And the reason why, well, it doesn't have to worry as much. And the reason why, they don't talk about this in the paper that I remember, but I'll give my interpretation. The reason why I think is fundamental to what I consider a kind of a basic shortcoming of previous diffusion model approaches, which is that when we take our image and then add varying amounts of noise to it, it looks like, except for the version where it's totally fully noised, it looks like, a sharp, the original image with noise on top. But during the reverse diffusion process, as you folks might have seen, when you take a very noisy image and try to denoise it in one step, you end up with this kind of like extremely fuzzy, kind of out of focus prediction. And then what happens during, the normal reverse diffusion is Gaussian noise gets added to that. And then we put that back into our UNet to do another step. Now, the fact is, this thing that it's putting into the UNet is out of distribution, which is to say, during training, our model never saw an out of focus version of an object with noise attached. So this is why it's very difficult for it to do it in a small number of steps, because you're actually giving it images that are out of distribution. It's never seen a fuzzy noised image before. For when you have quantized tokens, you don't really have that problem nearly as much. It's not predicting a kind of like a mean version of each pixel initially, because it's, it can't, it has to predict a category. And in fact, the way it works is that they actually use softmax over the predictions. So, and again, obviously softmax is very much encouraging it to like pick a category. So it's able to, like, they don't do anything special at all to allow them to use 10 steps, or sometimes they even try less than 10 steps. So 12 steps. You just don't have to be so careful about it because you don't have this out of distribution problem. And there are other ways to deal with this out of distribution problem, and most particularly the distillation diffusion papers, which basically say, okay, well, let's just train a new model kind of on the intermediate steps of a reverse diffusion process. So then explicitly these like noised versions of out of focus images are in distribution when you do it that way. Yeah, but with Paella, yeah, they don't really have that problem. And so I think that's interesting. And you know, another interesting thing about this, I guess this is kind of given how few resources and how little background these guys have, like they do a lot of things which I like, you know, like as simply as possible. So the model is a totally standard convnet. It has no attention. You know, there's very few of the kind of like state-of-the-art tricks in it. So I would guess that just like the original DDPM paper in 2015 wasn't that great, you know, either in terms of how long it took to run or what the outputs were like compared to nowadays. You know, I'm sure that there's lots and lots of room to improve this. I also like that they talk about their architectural search, that they, you know, used a really small latent space size and a really small data set, a Kaggle data set, what's more, which is really, to me, this is kind of best practice for building this kind of stuff. It's to yeah, learn as much as you can from rapid iterations, which they've done here. So yeah, as you can probably tell, overall, I'm enthusiastic about this paper. I think it's well worth reading and trying out. I think the actual Fed metrics presented in the paper seem to very significantly overstate how good it is. I don't know why or how that's happening, but like they're kind of putting it up in the table as being a bit of a, you know, maybe even a state-of-the-art approach, and clearly when you look at the results, it isn't. But I think it's very promising, and definitely makes me want to learn more about VQ-based approaches. And also obviously the fact that like Party and stuff use that approach, and Party generates some pretty fantastic outputs, also
Yeah.
makes me feel enthusiastic.
It seems interesting, especially because they got those results without even using self-attention. And that seems
Yeah.
like a clear win that you could just add it and automatically get better results, you know?
Yeah, exactly. And I should mention EleutherAI donated the hardware they used to train this. And I think this is a great example of the kind of paper that would never have been written, I'm pretty sure, without EleutherAI, because these people are not at any institution. They didn't have resources. So I think I would guess this paper only exists because of EleutherAI.
I don't remember exactly how. I don't know if you remember like the sort of, I guess, how the clip embedding is entered into the convolutional network. Is it simply, again, some sort of and I guess there's also like a time step embedding, right? Because like they do have some notion
They
of
do,
time steps,
that's correct.
but
Yeah.
so I
Yeah.
guess, yeah, how does, do you remember how that works? I don't remember actually.
I don't remember, but we can have a look at, so it's just here. So yeah, so you've got the noised indices, so the codes, the time step embedding, and the clip embedding given as input to the model as so. Yeah, where was the, actual architecture. Here we go. Oh yeah, I should mention like generally for VQ stuff, people use transformers, which actually does make a lot of sense because like transformers are all about, you know, kind of permutations and things. Does seem like a natural thing for that, but they argue that yeah, we don't want to use a flat 1D sequence because that's, you know, throwing away information we have. So let's do something with a 2D structure rather than having to kind of hack it in with positional embeddings, which I certainly appreciate. And they're also getting rid of the quadratic memory requirement. So they have a fully convolutional UNet with residual blocks. Okay, they're using depth-wise comms. Okay, so there's a linear projection for each block mapping the conditional embeddings to the latent dimension, which I think is pretty standard, right?
Oh, it was the modulated layer norm. That's what they did. Okay.
Oh, right. Yeah. So the modulated layer norm is a lot like that scale shift thing, but
Yeah.
they only have one parameter rather than two.
Yeah. Like, yeah, I guess when we talked about that, it was the ADM paper. So yeah, that must have been a few weeks ago, but yeah, I guess it was the adaptive group normalization, but this one uses layer normalization instead of group normalization. Yeah.
Yeah, well, it's kind of layer normalization. They also add, you know, a gamma and beta thing. So it's like a bit of a hybrid between layer and batch norm.
Yeah, I don't know, like, I guess they argue about the sort of 2D versus 1D thing, but like, I don't know, I guess, well, at least for like, if you think about like, you know, vision transformers, they do the same sort of thing, but they seem to be, you know, pretty comparable to convolutional networks, and in some cases better than convolutional networks. So I'm not sure, like, if, I don't know if it's necessarily and as important as maybe they are claiming it to be in terms of that.
Yeah, I mean, who
maintaining that 2D
knows? I think
structure.
like they came up with a premise and they tried it. And I don't know, like hopefully we'll get to talk to Dominic sometime soon, but you know, I wouldn't be surprised if just like apart from anything else, they're more familiar with convnets and
True, yeah.
UNets and ResNets and say, well, let's try that and see how it goes. Yeah, if you do the same thing again and replace them with VITs or whatever, maybe it would work better. I don't know. Worth trying.
Yeah, are there any other questions? Or it was like really useful that you gave like a whole background on both latent diffusion and VQGAN and this paper. It's like we covered 3 papers in one session. It's very impressive.
Thanks.
It looks like Molly had a question, but her audio is not working. I mean, if you want, you can type it out, or I don't know.
Oh, wait. The code book. So John asked if it's learned. Actually, I think something we noticed, Tanishq, is that in the Paella model, they do not reuse the VQGAN codebook, right?
Right.
They
Yeah.
create
Yeah.
their own codebook, which we found surprising. Yeah, so they learn their new codebook from scratch. So they use the VQGAN codebook to generate the encoded versions of the images, but then in Paella itself, because obviously you have to turn the tokens back into float vectors or reg3 tensors, if you like. Yeah, they have their own randomly initialized embedding matrix for that, which yeah, I would love to find out from Dominic why they did that, because it seems like it's making it much harder work than it needs to be.
I was also going to mention about like the I guess the Gumbel softmax trick. I don't know if I don't think you covered that.
Yeah, you should mention that because I am not ready to talk
Okay,
about it. It's at
yeah.
a very hand wavy level.
Well,
Other than that, I love it. It's Gumball's great.
My basic understanding, so let me see if I can find that section in the paper. Because they had it there. Where was it? Softmax sampling.
So while you're doing that, I'll just mention, yeah, the basic idea comes from a paper called Categorical Reparameterization with Gumball Softmax, which is a 2016 paper from Ben Pool's team. Lead author was Eric Zhang, which, yeah, in 2016, I remember there being an extremely high level of enthusiasm about the paper. And then for whatever reason, it never seemed to quite go anywhere.
A lot of people still use it for things. Diffusion has a Gumball a version that uses it to learn the code book.
Cool.
I think it was
Dali
here.
used it to learn their code book.
Really? Cool.
Well, so the basic idea of Gumball Softmax seems to be kind of similar to the reparameterization trick that we just talked about, but more for this categorical distributions. I guess the idea is that you can, so like with the, yeah, you can use this, there's this Gumball distribution, which is, I guess, some sort of distribution for categorical variables that you can use to, just like instead of with the reparameterization trick, you have the Gaussian distribution that you start out with, and you have some mean and variance. Here you can use the Gumball distribution along with the softmax of your, predictions. You combine those, and you can sample based on the probabilities from your from your after your softmax, right? So your softmax is going to give like probabilities for different different tokens, for example, and so you're using, now you can sample based on those probabilities using this Gumball distribution. So that's kind of the basic idea in a nutshell of what the Gumball softmax is. At least that's my understanding of it.
Gumball Softmax is a soft version of an old thing from an old paper which is called the Gumball Max trick. And what you did there is it's a fast way of sampling from a categorical. You take your logits for your categorical, which don't have to be normalized, add an independent Gumball distributed variable to each one, and simply take the maximum of the result, and that's how you sample. What Gumball Softmax does is it takes the softmax instead of the argmax, and it's reparameterizable.
Right. But so my understanding is like the softmax is used more for, let's see, okay, so softmax sampling, sample tokens. Right, so I guess, so I think one difference is that, I guess if I remember correctly, is this one, do you need a sample during training?
No, so the Gumball is not used in this paper at all. It's only used in the VQGAN paper.
Okay, right, okay. But they do
it's
okay,
trained
but they
with
use this
Gumball Softmax.
Right, okay. Okay, but here they have a softmax just to get the probabilities,
just
and then
the categorical.
Okay, and then okay, so the softmax to probability, and then we sample. Okay, this is just using multinomial sampling according to the probability. Okay. Okay. Yeah. And then I'm gonna point out something else which I've not.
Molly mentioned LTS as well, which I haven't
Oh
looked
yeah,
into yet,
yeah.
so I can't comment on.
Yeah, I also.
It kind of so unlike top K for language or Beam or some of the other techniques, it cuts off the very high probabilities and very low probabilities, so you get more interesting. I only glanced at the paper, but cuts off the high and low probabilities, so you get the more interesting or information dense possibilities. Yeah, tries to increase entropy, I believe is what it I only glanced at it.
So is it more to like, I guess, increase diversity of the samples?
That is my guess, just based off of what I saw, but they only mentioned it a few times and say they just
Yeah.
got better results using it. But what I wanted to say is it's interesting that you can use the when you use the vector quant VQGAN, you can use the language sampling techniques. Yeah, that's all.
It's weird though, because in these results, it doesn't seem like it says without LTS is what's giving the state of the art.
Yeah, and then in another part of the paper, they said they got better results for it. I only I looked it up and then I looked at their graphs and then saw they got worse results, and then saw they got better. I haven't pieced together where they got better and where they got worse. So, but yeah, the idea of using some type of top these other like language-based sampling mechanisms was kind of interesting.
Yeah, I'm a little bit confused why they say it's better when this. I mean, I'm not understand. Like, it says here with.
I have a
Okay, so
feeling that
here
they've
is
mislabeled their table. I think the bottom row is meant to be with
with.
CFG
Oh, okay,
with
yeah,
LTS.
that's a good point. Okay. Yeah, that's
Although,
probably
like,
it.
I'm
Okay.
having trouble, like, okay, so they say that with CFG and LTS, with CFG results in lie on 30K results in a 586% improvement, and with LTS results in a 187% improvement.
Yeah, I think it's just mislabeled because all the other, yeah, because these two are basically the same. So yeah, I think they just meant, okay, that makes more sense. Okay.
Oh, so the table is mislabeled. Yeah, that's why I was a bit.
That last one is, this last one is mislabeled because here it's without LTS with LTS, that shows an improvement. And then they were showing without CFG with CFG, that shows an improvement. And then they're showing with both of them, that also shows an improvement. But it's just that this one, it should be with LTS instead of without. It was just mislabeled.
Okay. Yeah, I had
That
looked
last
at
one
that
is
graph.
mislabeled.
I had looked at that chart and was wondering if I had misunderstood what they meant.
Yeah. Yeah, I think
okay, thank you.
Yeah, thanks for Jeremy. Thanks that Jeremy pointed that out. Yeah, there's seems to be a, oh, we should let them know or something.
Hmm.
Yeah, yeah, I guess. Are there any other questions that we should point out? Okay, if there are no other questions, then yeah, I think we'll conclude. Thank you again to Jeremy for, oh, sorry, was someone going to say something?
Oh yeah, yeah, I missed this before, but ever since I first saw VQVAE in what was the model? Oh gosh, a famous one. Okay, well, anyways, I always now think of it as words for talking for models to talk about patches of images was.
Yeah. No, yeah, like VQGAN, that's the thing, like this paper, and I think Jeremy mentioned this, was like, typically VQGAN is used for, creating tokens or these sorts of discrete sequences for, data that's not typically discrete, like, images and audio and things like that, that are like, you can't, I mean, they're technically discrete, but like, you can't, you can't, it's hard to represent them as, sequence of tokens, and the VQGAN and I guess VQVAE in general, because like, yeah, overall there's also like this, the VQVAE was also very similar. I think it's just, I don't remember the exact differences between, I think it's just mostly the loss functions are different, and like the VQVAE is different because, well, I think VQGAN is different because it introduces this discriminator loss in there. I think that might be the only difference between a VQGAN and a VQVAE.
I think that's the main difference. Yeah.
Yeah. But anyway, so VQ VAEs in general and VQ GANs are used for all these sorts of purposes where you want to take these sorts of more continuous data and make them into a sequence of tokens. So I think they're used in also, I think Jimmy mentioned it's used in Jukebox, which is like the audio model. So like taking audio and making them into a sequence of tokens, and then of course images, and usually they apply transformers because transformers are all for these sorts of sequence of tokens and those sorts of tasks. And so you see it like with Dolly Mini and Party. But this one was interesting because the VQ GAN is not being used for like passing into a transformer, but it's being used directly for this denoising task. So I found that kind of interesting because, you know, that's not what I would typically be using VQ GAN for, but it's kind of interesting to see this other sort of application.
Yeah.
Yeah, there's another question about the Gumball noise in the code. Let's see, Gumball noise, Gumball sample.
That's the Gumball max trick. It's not differentiable, and they're not backpropagating through it, so far as I can tell.
Oh, but the thing is, the paper. Okay, I see what you're saying here. Okay, Gumball sample, right? Okay, so this is a Gumball. This is a Gumball max trick. Okay. But then it's funny because it says in the paper, it says they're using the multinomial distribution and the softmax, right? But that that line
Gumball
of
max is a fast way of sampling from that gives you the same results.
Okay, it's funny because in the code
it saves you from actually having to do the softmax, which can be slow.
Okay. I see. Okay, because the code has the both lines, but it has one that's the Forge multinomial of the, you know, the output softmax, but that one is commented out in the code for some reason. And then it has the regular. Then it also has this Gumball max trick. So now I'm a little bit confused what they actually use in practice.
Well, they both produce the same distribution.
Oh, okay. They both produce the same distribution. Okay.
Yeah, Gumball max is just a faster way to sample from it that's like more parallelizable on a GPU.
Okay. Yeah, I guess I'm not very familiar with the categorical distribution sampling. So I guess it's something maybe I should look into more. Okay. Well, again, in that case, yeah, if there's no other questions, yeah, thank you again to Jeremy. And the plan for, I'm not sure what the plan will be for next week. I'll put a poll because next week is like Thanksgiving weekend. So a lot of the folks in America will not be available. I've already heard from some of you that you guys said that you're not going to be available to attend. So I may cancel it. But I'll put a poll out just to see how, what the interest is. And then the following week, I will be away at NeurIPS. So again, also, I don't know, maybe if someone else wants to host it that day, that's fine. Otherwise, again, that will also be canceled. So that's kind of the status right now. And I'll just keep everyone updated in the chat. So just keep an eye out for that. But just letting you know ahead of time what the situation is. So I'll talk to you everyone later, talk to you guys later. And hopefully this was helpful. And thanks again to Jeremy. Bye-bye, everyone.